Hi everyone. This is the fifth lab of EE533, and I'm Rohit. And we also have Hobo and Yukin here. So first, I'll take you through the ALU, how we have built synchronous ALU, and later I'll introduce to the elements of the pipeline like memory blocks and register files. Later, Hobo and Yukin will take you through. Uh, will will take you through the pipeline, how the pipeline works, and how it is implemented on the FPGA. Here, so on my screen, you can see the ALU Verilog code. So we have used a behavioral model to implement the Verilog. So and it's parameterized, uh, and it does basic arithmetic and logical operations. And this is my test bench to test the ALU. So I'm giving like random inputs to the ALU, and depending on the inputs, I'm capturing the outputs and comparing it with the expected outputs. So, and this is my simulation report. So this is about the like first part of this lab, and this is about the ALU. And coming to the next part, so that is about like memory elements, how we design the memory elements in the pipeline. So for the memory, we have used uh, block memory IP in the block memory IP. So if you can, so we have used data memory and instruction memory as a like block memory. So this is our IP of data memory. So where we have the width of the input and output port is 64, and it's 256 bits depth. So the reason for having like two ports, like two inputs and two output ports, is like we are interfacing this inputs with the hardware register, so that we can write the data through the code, like through the Perl script, which Yukwin will show later in the demo. So through the script, we were able, so this with these two ports, we were able to write the data uh, through one of this port, and other port we can read the data that's there in the data memory. So that's why we have like two ports. And similarly, this is our instruction memory. So in the instruction memory, we have uh, one port to write the instructions and another port that's connected to the pipeline. So this is about our memory modules that we have used in the pipeline. And now Hobo will take you through the demo and the working of the five-stage pipeline.
Okay, and thank you very much, Rohit. I will start it to show you guys five-stage pipeline and also do a brief introduce about you can make the register files. And let me first do the screen share. Okay, you can see my screens. And now, so our pipelines here, actually we can reduce it to five stage, but since the memory and these two memories, actually there's a typo here, it's a D memory. Since the I memory and the D memories are also the synchronized memory block, so it have another dummy stage here. So for to control this dummy state, we need to give our control signals actual registers. So there's mem and the red byte dummy state and also id.exe state. Actually, the register file we use here is the asynchronous read and synchronous write. So let me first show this part. Okay, so we can see that uh, the 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 rate signal, control signal is here. The rate is 0 and the rate is 1. So at very clock, it just operates the mux to do the data select. So actually, it's a combination logic. So it's asynchronous RAID. For the rat, it will need to synchronize the every flip flop. So it's a synchronous write. So we don't need a flip flop after a register after read. So it's another dummy state here. It maybe here's confused, but actually If we do the memory block here for the register file, it's need another clock as the I memory and D memory. So this is our 8-stage pipeline. And here's a code. For the code, it's also divided to a state, like the if stage. In the if stage, we control the PC and the PC debug for the output of the hardware to do the debug stuffs. And for if, we also have instruction memory here. We implement our instruction memory here to connect the PC into the data address for when we do the pipeline. Inside the pipeline, we used PC to as the in read address for when we're writing the instruction memory, we use the interface for the software. And in the FID stage, it's just a dummy stage. Okay, for the ID stage, we have our register files. So since the register file is asynchronous, as I mentioned like before. Actually, we don't need a register file, but we still add a register file here to just to align the all signals. So this ID stage, and after inside ID stage, we'll also implement the register files. Okay. So after the register files, we have ID and ES pipeline registers. This is the demonstration I mentioned here. So after this one, we have stage. So since this is a lab 5, right? So the lab 5 we don't have LU inside the stage, and I think in the lab 6 we will add the LU in this ES stage. We will use a rawhead design to do more uh the data operations here. So it need another clock. So we just it's actually another dummy stage here. Sorry, there's three dummy stage inside this pipeline. Okay, so next to ES stage is the memory stage. So inside the memory stage, we do the implementation of the data memory. And as Rahed mentioned before, we use the port B to do the software writing operations. We leave the port A for the pipeline, do the startward and loadward operations. And it's since it's a synchronized memory, it takes another clock. So we also have the control signals registers to align this clock. So the data and the control signal will be at the same clock to arrive at the WB stage. So in the readback stage, we also have another register after this register, the readback data and readback control will go back to the ID stage, right? Go back to the ID stage, go back to the register file to do the readback stuff. Okay, so this is the pipeline. And our group also have a pipeline test bench here. Let me show you the test bench. Where's the test bench? Okay, it's here. Okay, this is test bench for this pipeline. So it's also divided to several parts. The clock generations, okay, 100 megahertz. It's very close to our NetFPG. Actually, our NetFPG is 500 megahertz, and for the pipeline, we use the data pipeline, so it's a 125 megahertz. It's really close. So just for the test bench, I didn't design really close. So this is clock generations, and for the task, write to the M memory. First, we write load. Oh, this is a task. So I will do this task in the later loop. So this is a task to the program memory word, program write to the D memory. I just use the normal behavior for loading this data, like to pull up the enable and the write enables, and after that give the data, write the data to the registers so that we can do this programming and read the same thing, enable and write enable pull down. Okay, the PC reset. It's a pulse signal. It's a not level. Okay, and I have also a encoding helper function to give us more quickly to input our data to generate the instructions. like we use as we say we use the lower two bit for the register because our register file is only have four registers, so we only use two lower bit for this three data. So maybe we will extend it to four for have more registers. Okay, for the test sequence, we just reset all signals, then we program this data inside the instruction memory, and so that we can fetch them, later. And we also load the data inside. And oh, actually, this is the instruction memory. Sorry about that. Okay, this is a load instruction, writing program instruction into the instruction memory, and this is a load data, load 4 to 0, load 100 to 4, so that we can use it in the later. Yeah. And for the instruction is first a lowered, another lowered, and five no op, a six no op, and then to get the data from the B memory to store the four into the four. Yeah, why we have six no op here? Because we are eight stage pipeline. We want to avoid the to right after rate. Yeah, we want a wide read after array. So after do all this programming, we started run, like we set the run to one and repeat 20 clocks, and then we set run to zero and we check the memory, check the data. And this is for the test bench. Okay. Uh, okay, I'm sorry for taking a lot of time. I will be quick. And this is actually, this is a script for doing the loading the instruction by the software by the terminal to the NetFPGA. Actually, I should first do this part. Okay, do this part, and this is okay. This is one. So the pipeline actually is already designed, but to need to give the pipeline inside the NetFPGA, we need a top module. Inside the top module, we need to implement our pipeline, also the generic registers. This is to generate some registers for the software and both hardware so that we can check it outside to set some interface. So after we having this register, as I defined seven software and four hardwares, we can use this seven software to write by the software inside the NetFPGA and check the output of the hardware through these four registers. And after we define the seven and four registers, we can also we can also we need to define them inside this part like a 1, 2, 3, 4, 5, 7, 1, 2, 3, 4. Yeah, we have to define this to this so that the tools will help us to give the address for those registers we generated. So like we can directly write into them. If we don't have address, we cannot do that. So having this defined field, we will have this .h file. We can get the address. Okay, we can get address of this. So copy this address to, we can use this address, directly use this address to write into this register in the terminal. So for our convenience, we just copy them into this and do a script things. And I will not go very deeply through the scripts because it's just a script. So that's my part. So let you going to do the introduction about how to use the scripts and our own scripts to directly use the pseudo code, the assembly code to just use that script to directly write the instructions inside the NetFPGA and do the pipeline run test and uh, you can take a control.
Okay, I'm Yukun and let me check. I first share my screens. How to share my screens? I can't find that. Wait a minute. Okay. Uh, okay. Now, now I'll show you how we do the interface with the software and make the code easy to write. Firstly, it's that I log into the hardware and yeah, we could find that per code is in our NetFPGA. It's in yeah, this is our per code. We already uploaded to the NetFPGA. So what we need to do is we write a Python code that to interface with this per code that we send commands to this NetFPGA terminal that use the per code to do some instructions. And the whole logic, wait a minute, the whole logic is, yeah, because we don't add the ALU part, so we could only do very limited things like this. This is data memory write, data memory read, and software reset and run step and lower stop or send a nope. This is all iMemory writing. This is a basic mapping. So that we could write very easy code like this. Yeah, this is the whole structure of our lab 5. Like we first write the $0 with 4 and write $4 with 100 and then we load to the register 2, register 3, and after 3 knob we use one of their address and one of their data to write the $4 with 4. Yeah, this is the whole structure, and our Python code you could use like you could add comments like general C code, and it will ignore the blank lines, and it could support any 32-bit hex instructions. So it's really flexible to if you want to write something that generally we don't have then that word like. And the whole logic of our script is we first do a reset and then we will load our we will load the whole instruction into our hardware, and then you could. Okay, and then you could control it from your own terminal, or it will show a visualized terminal of NetFPGA. You could also do the instructions in there. And now we are showing our basic code. So this is for bit file. This is for our per script, and this is our command line. This one, and we could just run it and we wait for address not find. Wait a minute. Okay, yeah, so basically we this is our bit file. This is the command file you need, and this is the per script file in your hardware. And then after you typing all this, you could connect it to NetFPGA and write our all commands in the bit file, and it will things automatically. Like it will show all the commands translated here. And now it first do the PC reset and then it write all these command in here. Now could you could test commands from this terminal, but you could also type that. You could step and then after you do steps, okay. Sorry. What's the instruction? Okay. Okay, I'll try it again. Sorry about that.
One.
Okay, so now, yeah, this is the bit file. This is the command line you write here, and this is the per script file in your hardware. And then we run it all. It will firstly download the uh bit file, and it will do the PC reset, and it will write all your instructions. It will show that all the instructions translated. So you could write all the instructions here. Now you could type commands here or here. First we could have first try to do we do this write things. So we dememory read 0, and you will because we don't set this command on my Python script, so it will show that there's an unknown command, and it will directly send to here. So it's fine that you type some scripts that don't define in your Python. It will automatically send to this terminal, and this terminal will find it from its own scripts. So we could find that we successfully write 4 in the memory 0, and we could check about the memory 4. Yeah, this unknown command, so it will send that terminal, and will successfully write 100. And then we could do steps. We could do steps. Steps means you only run for 1 clock. Yeah, we could do some steps. And it's easy for you to debug. If you want to run it at a time, you could do run. Like we do 0 steps, and we could check the $0. We're writing to dollar four. We're writing to dollar four. Now it's still 100, and we could do one more step. Now, now we could check again. Yeah, now it turns to 4, means means our pipeline is correct. We successfully use the adjust 4 and the data 4 to write into the memory 4 with the number 4. And then and if you want to quit, you could just type Q, and then you will quit. It will Q or RKD. Then it will log out to this terminal. This terminal it's just for visualize, so that I show it. Uh, I could use a GNOME that you could do all the instructions from your own terminal. This is just for visualize, and maybe more easy for debugging. Okay, and that's all our work of the lab 5. Thank you.
Okay, great. Thank you, Yukun. And this script really save us a lot of time and give us a lot of convenience. And also thank you, Rohit. And for you guys, for the next lab, we will like merge the Rohit's ALU inside our pipeline to make it a real pipeline. So, and I will also paste our group's GitHub link after under this video. And thank you for watching.